All right, let's look at a common mistake in verifying an equation. All right, let's look at this example. Verify 1 plus tangent squared of theta is equal to secant squared of theta. Right? As you know, this is a true trig identity, so we should be able to verify it. Right? But here's a wrong way, and I've seen a lot of people do this. Right? So when you start out, you're going to actually assume the equation we're trying to verify. So we make an assumption that 1 plus tangent squared of theta is equal to secant squared of theta, right? So assuming what you're trying to prove, it doesn't sound very good, right? And then do this. And this implies that, so we're going to create a chain of implication to simplify both sides. So you have here, so we know that tangent is secant theta over cosine theta. So we're going to do that. So you have a 1 plus, right? So you have sine theta over cosine theta. And then we square the tangent. So I'm going to just put the square here and the square there, right? And then secant is by definition reciprocal of a cosine of theta. But you have to square that, so you put squared, right? So that's a true implication. All right, then what we can do is we can just take the common denominator here. So you have a cosine squared of theta. So 1 is same thing as a cosine squared of theta over cosine of squared theta plus sine squared of theta over cosine squared of theta. Right? So this is equal to 1 over cosine squared of theta. Right? And using the famous trig identity, cosine squared of theta plus sine squared of theta is equal to 1. Right? So which means that this implies that you're going to have a 1 over cosine squared of theta is equal to 1 over cosine squared of theta. So obviously this is a true statement because you got the left hand side and right hand side exactly the same. Right? Right. Seems like this is a valid proof, but actually this is a very invalid way of verifying an equation. Right. So here's why. Right. So this does not really prove anything, and if it was a valid method, we would be able to prove nonsense. For example, right? Let's try to verify 2 is equal to 0. Right? Obviously, this is not a true statement. We shouldn't be able to verify. Right? But let's use the same method here. Right? So assume what we're trying to prove. So you have a 2 is equal to 0. Right? Then we can just reduce it to something that's true. So we can maybe subtract 1 from both sides. So 2 minus 1 is 1. 0 minus 1 is negative 1. All right. All right. If 1 is equal to negative 1, then we can just square both sides. Then we get the 1 squared is 1. Negative 1 squared would be 1. Right. So we got the trivially true equality. Right. So it's done proving 2 equals 0. Right. So you can see that we shouldn't be able to prove 2 equals 0, and what we want here is completely wrong. So do not do this. This does not prove anything, right? So how do we fix this? Right? So one way is since the implication is kind of backward, so you have to start with something you already know is true. Then reduce it, use the chain of implication to say what we want to say, right? So for example, it's kind of an easy fix, right? So you can say that, see that here, 1 over cosine squared is equal to 1 over cosine squared. So we already know. So we know this. Right? Then implication should be this way. So we start with this, equality, which we know is true, which implies the statement above, right? So you replace 1 with the cosine squared plus sine squared, and then this equality implies the one above, right? 1 plus sine squared of theta over cosine squared of theta is equal to 1 over cosine squared of theta, right? So replacing sine theta over cosine theta with tangent and 1 over cosine theta with secant, we can come up with the equation we're trying to prove, right? So you should always start with something that is already true, then use the chain of implication to the statement you're trying to prove, right? So that's one way. And my favorite method is start with one side and then use the chain of equality to get to the other side. So for example, we can probably just fix this by doing this, right? So I'm going to erase assume. Then I'm going to write the left hand side. So I'm going to start with the left hand side. So you have a left hand side, right? Then we know that this can be rewritten as, actually left hand side is actually 1 plus tangent squared, just exactly what it is. All right, then instead of concluding that it's equal to secant squared of theta, we can use the chain of equality, right? So we know that this is equal to, right here, 1 plus, right, replacing tangent with secant of theta over tangent theta, we get this, right? Instead of making the conclusion right away, we can just say here, right? So I'm going to erase this, right? So we can use a chain of equality, right, chain of equality to write, right? So 1 is same thing as cosine squared of theta, plus you have a sine squared of theta over cosine squared of theta, right? Then you can conclude that this is going to be equal to, right? So again, this is just using a chain of equality equal to that. And then without saying that here, we're going to say, okay, now we know that this is equal to, right? Again, it's still a chain of equality. So this is equal to secant squared of theta, which is the right-hand side, right? Right. This is another valid way of verifying an equality or equation, right? So you cannot assume what you're trying to prove and to reduce it to something trivially true. That does not prove anything. So either you can start with the true statement and use a chain of implication to get to what we want to prove, or you can start with the one side of the equality and then use the chain of equality to get to the other side, right? That would be a valid proof, right? That's it. I hope that this was clear.